Okay? And this power is used to do two things. This is used to increase the kinetic energy, because I will have an increase from 1/2 m dot VA square to 1/2 m dot plus m dot F V jet square. Okay? And also, this is used to do something else. This is due to eat up the flow, because I'm starting from Cp m dot TA, and I'm reaching Cp gas, it's Cp air here, m dot plus m dot F T5. And there is also a small part that is lost here, which is 1 minus eta Cc multiplied by m dot F QCI. But that is, let's say, rather limited. Okay? And so, if you look at this, with, let's say, also some assumptions, for example, that this is small compared with m dot, you could say that you have reached, in fact, m dot divided by 2 V jet square minus VA square in the useful part of the fuel that is injected, because this is not useful and this is a pure loss. And so you could say first, I have created increase in kinetic energy. And you could define an efficiency that is equal to m dot divided by 2 V jet square minus VA square divided by m dot F QCI, where you have here 1 divided by the fuel to air ratio. And what is what you have there? You have an increase in kinetic energy. Okay? So this ratio is showing you how good you have been in increasing the kinetic energy of the flow from the entrance to the exit, thanks to this injection of the fuel. But you see that it's not the thrust, because the thrust is something else. The thrust is V jet minus VA. It's not the kinetic energy. And so you have introduced a first efficiency here, but this is not the final efficiency of the system we have created, because the system we have created is delivering thrust, not an increase in kinetic energy. This first efficiency, it is very similar to what we had in the eta E of the basic gas turbine cycle. This is what we call the thermal efficiency of the engine. You see why thermal? This is because the loss, let's say, is mainly due to the thermal loss, the eating up of the atmosphere that you have. And you see that T5 is lower with an adapted engine, so eta TH will be lower, will be higher with an adapted nozzle than with a saturated nozzle, because an adapted nozzle is a lower T5, so a higher eta thermal. And this parameter is a first one. This is showing, when you look at this equation, this is about a constant. The fuel to air ratio, this is about 1 divided by 60. So it's about a constant. It will maybe change a bit depending on the different working points. This is a constant. This is a constant. So what do we see here? This is purely function of V jet square. So, with this engine that we have invented, the turbojet, the first one that we have drawn, with a compressor, a combustion chamber, a turbine, an exhaust nozzle, and an intake with here a flow, we have created an engine that has as a first efficiency the thermal efficiency that is purely depending on Vjet square. So if you want to increase this, there is only one solution, this is to increase Vjet. No other solution. Okay. Then we need to look a bit further. What are we doing with this Vjet square? We have created kinetic energy, but this is not kinetic energy that we want to create. We want to create F. F can hardly be compared with the kinetic energy because F is a force. The kinetic energy is an energy. If you take m dot, this is a power. This is a kinetic power. So you need to transform this force into a power. How can you transform this thrust into a power? By multiplying this force by VA. At that moment, this is the propulsive force, because the thrust is what is pushing or pulling your engine and your aircraft multiplied by the flight speed. So this is what we will call the propulsive power. And the question is, what is the difference between these two? Between m dot divided by 2, Vjet square, which is a kinetic power, if we can call it like this. Of course, still minus the VA square, that was the initial kinetic power that was available. And so if we look at what is the difference between these two, we will understand where is the loss, what is the way, what have we lost between these two. And if we take F that is equal to Vjet minus VA multiplied by m dot, and if we multiply that by VA, we have the propulsive power, and the propulsive power will be equal to m dot multiplied by Vjet VA minus VA square. Okay? This is the equation of the propulsive power. And if we take this, which is sometimes called the available power, this kinetic power increase, because we have m dot instead of m, is sometimes called the P available. And if we take P available minus PP, what will we have? We have m dot divided by 2 Vjet square minus m dot divided by 2 VA square minus m dot Vjet VA. So if you want 2 divided by 2 minus, it becomes a plus, m dot VA square, 2 m dot divided by 2 if you want. And what do we see? We see that we have m dot that is everywhere present, and here you see Vjet square. Here we have plus VA square, and here we have minus 2 Vjet VA, so this is becoming something like this, and here you have Vjet minus VA square. So you see that not all available power, this kinetic power increase, not all this available power is used to create the propulsive power. you have this as a difference. What is this? This is due to the creation of this wake that you have behind the engine. You have a wake that is a V-jet into a flow that is at VA, because VA is much smaller than V-jet. And at the interface here, between the two flows, you have this kinetic energy loss between V-jet and VA due to the creation of the wake. And this is the energy that we have lost here in this term. And so you see that like this, you can define a second efficiency. The second efficiency, this is PP divided by P available. This is F multiplied by VA divided by m dot divided by 2 V-jet square minus VA square. This is, as we have PP here, what we will call the propulsive efficiency. The propulsive efficiency. And you see that we are losing, in fact, let's say in 2 steps. We are losing energy inside the engine through this thermal efficiency term. And in a second step, we are losing energy through the creation of the thrust, through the creation of the wake, by having a flow at V-jet inside an atmosphere that is moving at VA. And these are 2 very different efficiencies, I would say. Here, the loss is inside. It shows the eta th, very often it shows if we have a good engine. Here, it shows if we have the good engine in the right application. Because we see that here this is related with the aircraft that we have. So it's depending on the flight speed, VA. So this is only, let's say, an engine quality parameter. This is here an engine aircraft parameter. And of course, you need to have a good engine in the good aircraft. And at that moment, this is the product of these 2 that you need to consider. And this is what we will call the global efficiency, eta G. Okay? And this eta G is, as you can see, the propulsive power divided by the calorific power. This is the thrust multiplied by VA divided by m dot F QC